Okay, and so when it introduced to you and gave you the visual of those four fundamental forces, they're talking about those here in our notes. The four fundamental forces in nature are going to be your gravity, electromagnetic force, strong nuclear force, and weak nuclear force. And so, Landon, you move yourself today because I can already see that you're being annoying all on your own. So choose a seat right up here in front of me, in front of Garrett, or up here in front of Tristan. Pick one. 5, 4, 3, 2, there you go. Top. Waiting on you. I hadn't had time to get y'all in it yet. So Monday when y'all get back, it'll be projected on the board. Now, I need you to put your big spoon that you stir the stink with back in your back pocket or in your backpack. That's what I need. Okay, thank you. Now, when we were given the visual on these four fundamental forces, we were given the ability to talk about or saw pictures of gravity. There was electromagnetic force, which is stuff that we talk about with friction or with magnetism. Strong nuclear force is the force that holds the the atoms together, the nucleus of the atom together, protons and neutrons within that very extremely small space. And then weak nuclear forces are the actual forces within the atom itself that holds them together. So here's my question. Why is it going from velocity in section 1, acceleration in section 2, to now we're talking about forces? Okay. When we talk about forces, this is an action that causes motion. So if you apply force of some kind on something, it is going to change its motion. All right? When we talk about those four fundamental forces, gravity pulls us down. That changes motion. Magnetism, attraction and repulsion, changes motion. Friction changes motion because it slows objects to a stop eventually. Okay? Strong nuclear forces, weak nuclear forces, keeps atoms together as a whole. And so they work to keep the atom particles from disintegrating and moving apart from each other. So all of these things work together to talk to us about how that we are either going to maintain an original amount of motion, or we are going to have a force great enough to change the current motion that it's in. Okay? So that's where we're going with in this section. Yes, sir? Okay.
And I as well.
Yeah, I love giving y'all like extra packets every day. It keeps things fresh.
Thank you.
Okay, we're skipping this part because everything you need to know about those fundamental forces I just told you. When we talk about what these four fundamental forces are, we can then talk about how strong they are compared to each other. The strongest of the four fundamental forces is the strong nuclear force. It is the strongest force because if you think about how big an atom is, think about extremely how small an atom is. And then the nucleus is even smaller than that. It keeps those charged particles within a minute space. So it is the strongest of all the forces that we can experience. Then we have weak nuclear forces that are just below those. And it says here that they are 10 trillion times weaker than your strong nuclear force. So the force that keeps the nucleus of an atom together is extremely strong. Just next to that is the strength of the weak nuclear force that keeps all of it in together within the electron cloud and all that business. And it's 10 trillion times weaker than that one. So, pretty strong, right? Then next is your electromagnetic force. It's the third strongest. It holds electrons near the nucleus, It also is going to be contributing to us like static electricity, magnetism, friction. All of those things have to do with the electromagnetic force. And then the weakest of all gravitational forces is gravity.
Dang.
Think about that. I mean, gravity is pretty influential, right? So gravity is the weakest of those, but we can still at any point see gravity working. So that should kind of put into context. We will never grasp the true strength of a strong nuclear force, but it puts into context what we see from those things. And so it says that it is about 10 raised to the 40th times, I don't even know what that number is, weaker than the strong nuclear force. So we're going to carry on with the idea of these 4 fundamental forces with things that we can actually relate to and grasp their concept. Most of the time when we work with fundamental forces, with forces, we're going to work with contact forces. So contact forces are forces of objects that you can imagine have to be in contact with each other. Pushing and pulling. So when we have 2 objects that are going to touch one another, then we call those contact forces. The 4 that we just talked about, those are what we call field forces. Because you don't have to have 2 things in contact in order for gravity to affect you, or magnetism, or static electricity. Any of those things, you can have 2 objects that are not touching and still have the effect of those forces, right? So in the process of looking at all those, let's talk about how that we are going to experience a contact force. Ultimately, the one thing that I want you to get from this entire lesson is that forces act to change the motion of objects. We are going to do some sort of push or some sort of pull on an object in order to change its motion. So we look at an overall, what we call net force on an object in order to do that. Brody, do I need to have you move your location as well?
No, ma'am.
Then stop it. I'm working on a timetable here and y'all are screwing it up. Now, when we talk about pushing and pulling on an object, your net force tells you if you're going to see a change in that particular motion. A net force, do you remember how that we add and subtract those velocities? Like if you're going east and west, you subtracted those 2 to get an overall velocity. We did that in section 1. Or we were going north and south and we subtracted them. Or what about if we were both directions were going east? You added them together, right? So we're going to do the same thing for net forces. That's why it's saying it's the combination of all those forces acting together. Combination meaning that if you have 2 positive forces, you add the combination of those forces. If you have opposing forces, one going left and the other one going right, then you're looking at those, combining those by subtraction, okay, to get a net force over the entire thing. We will work on saying that an object will accelerate if it has a net force acting on it. It will have a change in motion if it has a net force. But the object will not have a change in motion if the net force is equal to 0. So let's look at some pictures to describe that. These pictures right here are going to describe what those last 2 sentences were that we just underlined on the previous page. When we look at that top picture, in physics, we use these force diagrams like this a lot because it's a whole lot easier for us to actually describe motion based on an arrow than it is to actually draw an elaborate picture, okay? So they're combining these 2 things just because this is the first time that we've used it. When you see arrows in physics, arrows are going to indicate direction. That's kind of a no-duh point. But also, we're going to use them as like a magnitude, which means the size. If you look at those arrows, can you tell direction from them?
Yes.
Yes. And can you tell, are they the same size?
Yeah.
That means that that's the same amount of force. That's the magnitude. So if you were to look at that top picture, you have a force going to the right, you have a force going to the left, and those appear to be the exact same values. So how would you describe that net force of both of them? Zero. Yes. And we can also look at this as values of 5 newtons of force and 5 newtons of force. So if we have a value of 5, how would you differentiate between the two? Same way you did with the velocity. The guy that's pushing to the left is a negative 5 newtons. The girl that's pushing to the right is a positive 5 newtons. So if you were to mathematically prove this force, you would be able to say positive 5 plus negative 5 gives you 0. We call this a balanced force. A balanced force is going to be one that has a combination force of 0. If an object experiences a balanced force, it will not change its motion. It doesn't change at all. So does that mean that it's going to say that it's going to like make it go to rest? No, it does not. When we say that that object is at no change in motion or no acceleration, that means if the object is at rest, it's going to stay at rest. Or if the object is in motion, it's going to stay in motion because we're not changing anything about it. Follow that example? So don't think that the object is going to have a net force of 0, so it's not moving at all. An object can be moving and have a net force of 0. Okay? Next picture below that one. How do we see a change in the motion of this object now?
It's going.
I have, like, let's just pretend I only see one arrow, right? So that's a combined force, magnitude going to the whatever. Isn't it weird how my eyes have looked forward this entire time? Isn't that odd? Wonder if your eyes can do that. I triple dog dare you for your eyes to look at that board the entire time we're in here. Listen, no man has ever let themselves down on a triple dog dare. Not saying you're not a man. Just saying. Triple dog dare.
Sounds like a challenge.
Mm-hmm. Nope, you've already lost. Now, when I look at the magnitude of this force, you guys understand the arrow concept. But now let's put the values with it again. If we say that these two people, just based on example, this guy's pushing with 5 newtons, this lady's pushing with 5 newtons, how does this example now play into the part of direction of the force? Well, they're both pushing to the left, so that's a -5 and a -5, right? And then how would you tell me what the value of that net force would be? -5 plus the -5 would give me an overall value of -10 newtons. Now, does that mean, does that mean it's a deficient, like 10 force or 10 newtons of force, or what does that negative mean to us? Okay, so we're still pulling from section 1 with the direction, right? It's going to the left with a value of 10 newtons of force. When we look at that, do you feel like this couch in that example is going to have a change in its motion?
Yes.
Yes. Is it going to see a change in speed?
Yes.
Yeah. We are assuming, based on this picture, that the couch begins at rest. But now, we are assuming, because it's telling us with this top arrow here, that it's going to have an acceleration, that is going to have a change in its speed, and it's going to go from rest to actually moving. The only reason that we go ahead and assume that it is going to have an increase in its speed is because we have a value of force greater than 0. Okay? That's why I said that comment to you about how that this is not necessarily a negative 10, as in negative 10 being less than 0. That negative is going to say only the direction. Okay? Underneath this picture, your description of net force is saying that when the net force is acting on an object, it is greater than 0. The object will accelerate in the direction of that net force. So if you ever do your force additions like we've done, you're always going to be able to say, if I have a force of greater than 0 in a positive or a negative value, I see a change in that object's motion. Okay. We can have a system of fundamental force, though, that can oppose motion, and that is called friction. But your two objects have to be in contact in order for you to have friction. So that couch was sitting on the carpet, right? It's going to have friction applied to the legs or whatever's of that couch is touching the carpet. Would it be easier to slide that couch on carpet or like on tile or linoleum floor?
Tile.
Okay, so let's talk about why do you experience less friction on those surfaces. When you think about carpet, I want you to get really silly in terms of how specific we're talking here. Don't just think about that the carpet looks kind of fuzzy. I want you to go down and think microscopic level of those fibers in the carpet. Okay? Every one of those fibers is touching the bottom of that couch. Every one of them. So, if every fiber is applying a friction to that object, do you understand now why that it would be easy to say that it opposes the motion of it moving on the floor? Yeah. It moves so much easier on linoleum or tile flooring because you don't have individual fibers that are touching the bottom of the objects. You don't have as much resistance because of those particles interacting with each other. Okay? So when we talk about friction, you just have to know, number one, it only occurs when two objects are in contact. And number two, depending on the material that is in contact, we're going to see different amounts of friction. It even says here, the rougher the surfaces, the greater the friction between them. From a pre-AP standpoint, when you have friction, you have heat that is produced. So why does it actually take away from the motion of the object? Heat is a form of energy. And so when you have two objects that are in contact with each other, instead of all the energy of that object going into kinetic motion, which makes it go, some of that kinetic energy is converted over into heat. As you take away from the kinetic energy, it turns into heat. The hotter that you get, or the more heat you get from the friction, the less kinetic energy you have. So think about it when you were little, or if you saw kids playing with those little Tonka trucks or Matchbox trucks, cars, and they rolled them across the carpet. They would roll for so long, and then eventually they would slow down and stop. So now I want you to think about it as when that kid was playing with that and let it go right out of its hand, it had the most amount of kinetic energy. But the longer it stayed in contact with the floor, the more friction that occurred on that toy. Do you agree with that?
Yes.
So, the more friction that was applied to that, remember we're saying that it's heat? You may not feel the heat, but that occurs. The heat energy is being taken from the kinetic. And what happens when you eventually have the kinetic energy that's gone? It stops. So that's why we see a decrease in motion when friction is applied. Gives you an example here of friction is why that we have this this match that is struck. There's friction between the match head and the surface, like of that sandpaper that's on the side. The friction produces heat. The heat causes the flame of the match. So, cause and effect. So, why do we have friction here that is going to actually... How do we see motion when we can still know that there's friction occurring? Rephrase that. When you have friction, there are two types of friction. There's kinetic friction, and then there's static friction. Kinetic friction is just exactly like kinetic energy. Two objects that are touching, but you still see motion. Okay? Rolling friction is a type of kinetic friction. Sliding friction is a type of kinetic friction. So as you're rolling along, you see the truck that's going along the surface of the flooring. So when it's rolling, it has kinetic friction because it's still moving. But like Louise said a second ago, it finally gets to a certain point and it stops moving. That is when it has converted itself to static friction. Static friction is when that you have friction that has met its highest value and opposes the motion. Static friction is greater than kinetic friction, and so just like two opposing forces, whichever one is greater is what we see in terms of motion. Static friction can be so great that it stops the motion of an object.
Wow.
In most cases, it takes a greater force to start an object moving than it does to keep it moving. My favorite example of static friction, because it has the best visual, think about if you were going to go help somebody move and you had to move something extremely heavy, like a freezer or a refrigerator or like a couch. You guys ever experienced something like that?
Yeah,
Even if you're not moving. Let's just say your parents want to vacuum or clean behind it and you have to move it out for them. It's really, really hard to get those heavy objects moved. You have to apply a greater force at the beginning than at the end. Do you know why?
Because it has stagnation.
Well, that object has stayed in place for so long, the gravitational force has really gotten a hold of it. You have a high amount of static friction there because the object isn't moving. So you have to apply a greater force to start it moving at the beginning because you have to break the kinetic friction. Once you get that kinetic friction broken, isn't it easier to slide it out after that initial put or initial force? It's a whole lot easier to push and pull after that initial part. Usually static friction is shown like because the object's so heavy, like you can see the indentions of it in the floor after you move it.
Oh, yeah.
Right? That's a good indication of that static friction. We also have friction in everyday life. Like, for instance, the two examples I always use about this. I have a fundamental force of gravity pulling down on me right now, right?
Yeah.
But am I falling through the floor? No. The building itself is engineered in such a way that the gravity that's pulling me down is also counteracted by a force that's pushing back up on me. And it's happening to you too because you're not falling through the floor.
Yay.
Now, in the process of us doing that, we are able to actually sit here without falling out of our chairs, and I'm able to stand here without slipping and sliding around on the floor because we have friction that is, I guess, maybe applied to us at the exact same time that the forces are applied. When you walk across the floor, the whole reason that you can take a step without falling on your butt is because you have friction on the bottom of your shoes. So we incur friction every day. Another way that we also incur friction is when we have things like objects with fast-moving parts, like an engine in a car. Why is it necessary for us to keep oil in our engines of our cars?
So there's not too much friction in it.
Years.
Okay, so in girls, one thing your dads are going to tell you when you start driving, make sure you always check the oil. because you don't want to actually go on some kind of long trip somewhere and then all of a sudden your engine blows up. Now, so why is this important to us? Because all of us will eventually either ride in a car or drive in a car. When you have oil inside of your motor, what you're doing is you're helping everything run smoothly. Do you feel like the parts of your motor are touching?
You gotta, yes.
Yes. We say every time something is in contact, it has friction. Would you agree?
Yes.
Every time we have friction, we cause heat. We know from our chemistry section that the more heat that is put onto a metal, the more fragile it gets, right?
Yes.
Because the molecules are moving so fast, they try to get out of the way from each other. Now, in the process of doing that, the higher the heat gets within inside our engine, the more that metal wants to move. If we keep oil as a lubricant inside of that machine, what we're doing is we're helping all of those gears, all of those pistons slide up and down in the cylinders and all of those things. We keep all of that running smoothly. So, gives you the walking around example of friction. You have driven in a car at some point today already. That's another way that you're always using friction. These examples here that we will get in each chapter is why that I was telling you when we started this physics section. You have physics in everyday life, just like you had chemistry in everyday life. You just may not have ever realized that that was actually physics, okay? We're going to try to pull an everyday example from every one of these chapters.